Welcome back everybody to our course on memory device technology for AI/ML computing. Before we jump into today's topic, let's do a very quick recap of what we discussed in the last class, where we began our last module and we introduced spiking neural networks, or SNNs. So we started by talking about why do we even need spiking neural networks. And we saw that is mainly because they offer a huge improvement in energy efficiency, which was expressed in terms of watts per TOPS. And we saw that spiking neural networks, by the virtue that they are much more bioplausible, they offer this advantage of having much lower watts per TOPS. And that was the primary motivation. Then we saw that although ANNs and SNNs can essentially have the same network topology, but what happens inside each node is very, very different. In ANNs, what we have been studying, the inputs are continuous valued functions, activations are smooth, ReLUs, or sigmoid functions, and the whole process is designed for supervised learning, backpropagation algorithms. However, in contrast, the spiking neural networks, the inputs are essentially discrete spikes. They are neurons which are firing abruptly when the membrane potential hits a particular threshold. And more interestingly, spiking neural networks hold a lot of promise because of the possibility of having unsupervised learning, much like what happens in our own brains. After that, we looked in detail at the leaky integrate fire model, especially from a perspective of writing the pseudocode. And that helped us in seeing how the spiking neural networks essentially help in event-driven computation. Neurons resort to firing only when there is actually some activity happening. So we saw the pseudocode, and also we run the pseudocode to see how for a bunch of 3 inputs having 3 different weights, how the output activity is much sparser than the input activity. And this sparsity, along with event-driven computation, which is very close to bioplausibility, is the reason why we have the promise of very low power computation in SNNs. Finally, we also discuss the different encoding and decoding schemes, basically how you translate analog real-life information, pixel intensities, speech data, into spike traits. Because as we discussed, spiking neural networks only understand 1 or 0, just spiking events in time. So we looked at rate encoding, where the firing rate just depends on the pixel intensity. And also we looked at temporal encoding, as you can see over here, which encodes information based on the timing of the spike. So this is what we discussed in the last session. In today's session, we are going to look at a very, very interesting question. How do these spiking neural networks actually train? And we will see that although the actual promise of spiking neural networks is in unsupervised learning, it has certain limitations. So we will also look at supervised learning. So let us look at what we will be studying in detail today. So as I just explained, although SNNs primarily were developed so that you can have unsupervised learning, as we will see very soon, that has certain inherent limitations in terms of scalability and accuracy. So although first we are going to have a deep dive at unsupervised learning, we will also see some supervised learning techniques. So let's give a brief outline of what is unsupervised learning in principle. So as you know, unsupervised learning comes from the idea that how do you imitate how biological neurons learn through local interactions without any labels, without any global loss function, just with spike timing. And the most common rule we have studied in detail is known as spike timing dependent plasticity, where dependent on whether the pre and post synaptic neuron is firing in a correlated manner, Pre is firing before post, or vice versa. You can either have a long-term potentiation, that is increase in the synaptic weight or the strengthening of the synaptic weight, or you can have a long-term depression, which is a decreasing or de-strengthening of the synaptic weight. So if you don't remember, here is a quick recap. If you see, the presynaptic neuron over here is receiving signals from three inputs, I1, I2 and I3, and the firing sequence of I1, I2 and I3 are given. And as you can see, I1 and I3 events are totally correlated events, because only after I1 fires, O1, which is the output spike, is firing. Similarly with I3, which fires just before the firing of the output O1. So we can say that I1 and I3 are correlated signals, and therefore there will be a strengthening of the synaptic weight. But important to know that the strengthening of I3, which is delta W3, the synaptic weight corresponding to I3, will be much more, because of this exponential function. The smaller the timing difference, larger is the strengthening. Similarly, because I2 fires after O1, there will be a de-strengthening of the synaptic weight. So this is a very quick recap of what spike timing dependent plasticity is. So as we will see in our next slide, all the learning that happens in unsupervised training primarily is dependent on such local Hebbian rules like STDP, but also there is added spice from other bioplausible techniques like lateral inhibition, homeostasis, so on and so forth, which we will see very soon, which improves the performance of these networks. Okay. Next, we will look at supervised learning. So we have been discussing what are the challenges in supervised learning, especially in the context of spiking neural networks. So remember, in spiking neural networks, a direct application of the back propagation will not work. Try to recall why that is the case. Because when you do back propagation, your activation function or your thresholding function cannot be an abrupt function. This is because abrupt functions, all or nothing, spiking, these are not differentiable. And differentiability is a very important aspect of implementing backpropagation. So how do you circumvent this problem? You circumvent this problem primarily through this technique called surrogate gradient learning. And this is what we will look at in today's class. And also there is another method where you take a trained deep neural network and you convert it into a spiking neural network. Now this is not really learning per se, but it is also a way to expand the scope of spiking neural networks. Although this method you can only use for inference-based tasks. Only a trained deep neural network can be converted into a spiking neural network. So it may not be classically very correct to say that it is form of supervised learning, but nonetheless, I hope you get the flavor or the idea. Okay, with this background, let us begin by looking at unsupervised learning in spiking neural networks. And although there are many examples of unsupervised training in spiking neural networks, what I would like to do is focus on the first seminal work which came from ETH Zurich, which showed that using STDP, learning is very much possible for small tasks in spiking neural networks. But it is important to suggest right at the beginning, all of this was demonstrated only in software. Okay, so this was based on code. So in principle, you were able to show these things. So first, let's look at the input and output encoding scheme. As we have discussed in the previous lecture, mostly input and output encoding happens through this Poisson spike train. But before that, what are we encoding? We are encoding the MNIST image. I hope you remember what is the MNIST data set. It is a bunch of handwritten digits, roughly 28 cross 28 pixels, and each pixel intensity will be then converted into spikes using rate-coded Poisson process. So we had already discussed in our previous lecture that rate encoding essentially means that the rate of the spikes over time is proportional to the pixel intensity. But what about the interspike timing? That follows something called the Poissonian distribution. This means that the events or the interspike distance are actually random. They occur with a Poisson distribution. So this kind of distribution is used over a simple uniform distribution where all interspike distance are same, because it captures the observed irregularity and inherent randomness or stochasticity in the real neuronal firing. But why does that help us? It helps us because it gives a lot of robustness to the network. Why? Just imagine, if you had to denote 255 pixel by uniform spiking, there is only one way to do that. However, if you include some interspike distribution, if you include a distribution in the interspike timing, there are many ways of representing the same pixel data. And this helps in building redundancy and therefore also robustness. And you will see that this is a very regular feature in biologically inspired computing, the trade-off between redundancy and robustness. And this is how the static image is transformed into a dynamic stream of spikes, as is being shown in this particular slide. Now let's look at the network architecture. The network architecture is rather simple. You have your input layer and just one output layer. Actually, the output layer consists of two mirror layers. So these two sub-layers are called the excitatory layer, which we will call as layer 2A, and inhibitory layer, which we will call as 2B. What does this layer consist of? They are simply made up of leaky, integrate and fire neurons. I don't need to again explain what are LIF neurons. Keep integrating in a leaky fashion and then fire when it hits the threshold. So the important question at this juncture to ask is, where does each of these neurons take its inputs from? And this is where we introduce the concept of it being fully connected. That means that each input neuron is connected to an excitatory neuron by a bunch of weights. So what that means is each pixel of this particular layer is connected to the pixel in the excitatory layer as well. There is a little bit more complication in how the output layer or the excitatory layer is connected to the inhibitory layer, and that is what we will discuss in upcoming slides. So I hope you understand the input and output encoding, which is rate encoding with Poissonian distribution, and the simple network architecture. Next, we will look at how the network is operating or how is learning happening. So this is based on 4 different brain-inspired concepts. Let us look at them one by one. The first brain-inspired technique is the weight updation technique, which is happening through spike timing dependent plasticity. Now, we have discussed spike timing dependent plasticity several times, so we don't have to again go into the details. If there is correlated firing, the synaptic weight is increased. If there is uncorrelated firing, the synaptic weight is reduced. However, there is a very important concept which is now getting added in addition to spike timing dependent plasticity. That is the fact that the weights decay to the baseline when no activity happens. Why is this the case? This is because in biological systems, synapses which are not actively used tend to weaken over time. This is a form of homeostasis or balance. Now, homeostasis is a very important biological concept which enables the ability to forget and therefore better resource optimization. Let me give you an example. If you remember everything that you see in a day, soon your neural connections will get totally fired. So whatever is relevant according to the brain, like the number plate of your car, you will remember for a very long time. Why? Because you are remembering it many times. But the number plate of the Uber that you have hired to just go to the airport or somewhere, you will just remember for a very short time, right? This is the idea of homeostasis. So here also, If inactive synapses were allowed to keep their previous strength indefinitely, the network would lose a lot of adaptability and would saturate with noisy or even outdated information. So this weight decay mechanism ensures that connections that are only repeatedly used are active, and the ones which are carrying meaningful spike timing correlations remain strong. So it's a very important concept of resource optimization. Next, let's look at the second very interesting bio-inspired concept called lateral inhibition. And this is where the connection between the excitatory layer and inhibitory layer comes into the picture. Now let us understand how that is happening. So each excitatory neuron that is in layer 2A is connected to the corresponding layer in 2B. That means each LIF neuron here is connected to the corresponding neuron in the inhibitory layer. So that is a one-to-one connection. So there are n one-to-one connection between these two layers. Now that is not the end of the story. The inhibitory neuron in 2B is also connected back to all the excitatory neurons, except the one that originally activated it. What that means is this particular neuron is connected to all other neurons in the excitatory layer except the corresponding neuron. That means for n neurons, you have n into n minus 1 connections of these lateral inhibitory connections. What this achieves is essentially competition. When one excitatory neuron, let's say this particular neuron, fires, it activates its corresponding inhibitory layer in layer 2B. And that inhibitory neuron then suppresses all the other excitatory neurons in the layer 2A, allowing only that corresponding neuron to dominate for that input. In other words, it is like the network saying, let me have the bread this time. Suppose I'm teaching in a class and every day I distribute only one piece of chocolate. Now, if I throw the chocolate and everybody wants to fight over the chocolate, every day, every person will get very, very, very little chocolate and nobody will be satisfied. But if all of us decide that today let me catch the chocolate, I will have it completely for myself. Then tomorrow I will just keep shut. So that is the strategy that is being employed in our biological systems and also in this particular work. And with the same principle, the third brain-inspired principle here that is used in this network is homeostasis, but in a different fashion. And you will see how this homeostasis ensures very efficient use of physical resources. Now, let us imagine that for one training cycle, and this is homeostasis being implemented with different training cycles. So imagine one neuron has already learned a particular pattern very, very well, and it fires often and dominates during one particular training. Now, if we allow that to always continue, the same neuron will now keep winning every time and the others would never get a chance to learn. To prevent this particular effect, this homeostatic mechanism is not only introduced, like we discussed earlier, in the weight update mechanism, but also between training cycles. And how this is done is that once a particular neuron learns, it increases its firing threshold. So when it increases its firing threshold, it means that the neuron is less likely to fire, and therefore it allows other neurons also to participate in the training process. So you can think of it as the neuron saying that I have already have my share of learning a particular pattern, let others learn also. And this is what keeps the network learning balanced and encourages a lot of diversity in learning and makes it much more efficient use of available neurons. Now, one important concept to understand was how many neurons are actually available at the excitatory and inhibitory layer. So the number of neurons which was available in the excitatory layer and the corresponding inhibitory layer was anything between 20 cross 20 to 80 cross 80. And what was seen is that as you increase the number of excitatory layers, the accuracy keeps improving. Why is that the case? And this is the final brain-inspired concept that is being used, and that is the concept of using redundancy. So as you know, even in the brain, the same information isn't stored in a single neuron. Instead, many neurons represent overlapping features. This redundancy is what makes the system very robust. Even if some neurons fail or misfire, the information is still preserved. In this particular work, the same idea is reflected over here by the concept of 2D receptive fields. So as you can see from these 2D receptive fields, the numeral 2 in its different manifestations are getting mapped to several neurons, all having little bit of variations. This not only improves the fault tolerance, but also increases the chance that network can correctly recognize a noisy or distorted input. In this case, the distorted input will be different strokes of writing the same numeral because these are handwritten digits. And the results on this particular graph show that as we increase the number of excitatory neurons, of course, the amount of weights in the system is also increasing, the complexity is also increasing, the accuracy steadily improves to almost 95% when you have the highest number of neurons, which is 80 cross 80 or 6,400 neurons. And that makes a lot of sense because more neurons mean more parallel feature detection. Just having multiple specialists working on the same problem. And this concept of having more redundancy in the system also increases the amount of resources that is needed, but also it increases the accuracy of the network. So overall, this concept of spiking neural network is truly bio-inspired. But if you look at the percentage of accuracy, 95%, for a simple task like MNIST, it was soon realized that there are going to be some inherent limitations. And that is what we will discuss in the next slide, where we will do a brief review of all the improvements in unsupervised spiking neural networks after the first work in 2015. Now, it is not possible or necessary to go through all these works in detail, but what we can see is that some very important trends emerge by doing this very quick study on the kinds of unsupervised spiking neural networks. So let us look at what are the important trends that emerge from reviewing the different kinds of unsupervised training in spiking neural networks. The first thing that we see is that after the first work by Dial and Cook from ETH Zurich, there were many different works which showed better and better bioplausibility. While Dial and Cook, just we discussed, relied mostly on STDP and lateral inhibition in addition to homeostasis or adaptive threshold, when you start tuning the kind of STDP called winner takes all, using rank order encoding, and also using other more richer neuronal dynamics, you were able to improve the accuracy of these neural networks from 95% to almost 98 to 99%. The second thing we notice is that although the early workloads is static MNIST data, mid to recent works have shown an expansion into event-driven tasks with both spatio-temporal richness in the data. And that shift is very important because unsupervised STDP naturally exploits timing. So moving to spike timing rich data plays to the strength of spiking neural networks. And you will not only see improvement in accuracy, but also robustness to all kinds of temporal jitter and motion. So this is a very important feature of unsupervised spiking neural networks. The third thing is not very encouraging. What we saw is that although to get better accuracy, the architectures progress from single competitive layers to little bit of multi-layer feature stacks, improving accuracy becomes very, very difficult, because here learning is purely local and there is no global loss function to shape what should be the and what will be the impact of the weight updates in later layers or advanced layers to the early layers. And yet, though accuracy improves, depth and parameter count remain very, very limited, because learning is purely local and there is no global loss to share these deep hierarchies. And that is why even the best entries in the results show that the accuracy of the spiking neural networks are way below your deep neural networks. And finally, as we will see in the next lecture, the hardware implementation of spiking neural networks, especially the full-scale analog hardware implementation, has been very, very rare. Early results tried to use STDP from PC RAMs to mimic spike time dependent plasticity, but the implementation of spiking neural networks was still done only in software. So with this, we are motivated to look at another kind of training, which is called the supervised training. So as we discussed, in supervised training, we have two main strategies. The key strategy is using surrogate gradient learning, and that is what we will cover first. So as we have been discussing in detail, the key issue with directly using backpropagation for spiking neural networks is that, if you remember from our 7th module, the chain rule which was implementing backpropagation had a very important term of differentiability of your activation function. So your activation function needs to be differentiable. However, in spiking neural networks, a spike is simply a binary event. It translates to the fact that the derivative is almost zero everywhere and really undefined during the firing threshold. So standard backpropagation algorithm just cannot work. And to solve this conundrum, researchers proposed something really interesting. It was a very smart trick, and this is known as surrogate gradient approach. And the idea of surrogate gradient approach is very neat. In the feed-forward pass, as shown in the left-hand side, the network behaves just like a real spiking neural network. Each neuron is characterized by the abrupt thresholding function. But when it comes to backpropagation, you just keep everything the same and only replace this abrupt thresholding function with a surrogate or a smoothened function during the backward pass or the backward propagation stage. And this surrogate function, by the idea that it is a smooth function, allows these gradients to flow backward through layers and through time. And this approach gives us the best of the both worlds. This approach preserves the energy efficiency and the event-driven nature of spiking neural networks during forward pass, but also enables gradient-based optimization like in ANNs in the backpropagation. And this is what has become the standard method for training deep and scalable supervised spiking neural networks today. Now let me explain that with two recent examples. On the left-hand side, you see a major milestone which came in 2021 with the work of Fang et al. Before this paper, most spiking neural networks were relatively shallow. Maybe they were just a few layers, because deep training was unstable and gradients tend to vanish. But this work completely changed everything. What they introduced in this work is something called a spike element wise block. The idea was to take residual connection principles from standard SNNs, the same ones that were used to design the ResNet, and redesign it so that they can work within spiking dynamics. And this innovation preserved the gradient flow even across hundreds of layers, solving the long-standing problem of vanishing gradients in deep spiking neural networks. And as you can see in this particular graph, you see that the spiking ResNet in blue and green maintains stable and high accuracy compared to the plain networks in red. So using this surrogate gradient descent, they were able to directly train spiking neural networks, and they were able to achieve state-of-the-art performance on complicated data sets like CIFAR 10 and CIFAR 100, which has been very, very difficult, or rather impossible, with unsupervised learning. Next, we look at another very neat technique called learnable surrogate gradient algorithm, which was introduced in 2023. And their key innovation is that they recognized a key limitation in the standard surrogate gradient training. Let us understand this by this particular graph. As you can see, a standard activation function in SNN will be an abrupt function. So in surrogate gradient descent, as we just discussed, it has to be smoothened out. But you can see that you can smoothen out by using a sigmoid function with different standard deviations. So a standard deviation of 2 will have a very broadened out gradient function, whereas with sigmoid with sigma 8 will have a very tight gradient distribution. So the question they asked is, when we convert this abrupt function to a gradient based function, which sigmoid should we use? And they were able to show that if they use one of these sigmoids, that is not optimal for all the layers. So what they introduced is the dynamic adjustment of how sharp or smooth the surrogate gradient function behaves like. And this dynamic adjustment preserves the gradient flow through deep neural networks and reduces the errors. And as that is shown in the figure, this learnable surrogate gradient, where not the same sigmoid is used across all layers and it is learned which is best for that particular layer, pushed the accuracy of really complicated data sets like CIFAR 10 to CIFAR 100 quite significantly. But more importantly, what they were able to show is that they are able to get this accuracy at much smaller number of epochs. That is, they can train the network effectively with much lower number of training cycles. So together, these represent two key breakthroughs that proved the point that making supervised SNNs both deeper and more accurate while staying true to the event-driven computing paradigm can really help scaling spiking neural networks for low power AI/ML tasks. So as we had discussed, there is another technique of training which involves taking a trained deep neural network and converting it into spiking neural network, but that we will leave for the next class. So in today's class, we saw two very important ways of training the spiking neural network, that is by using unsupervised STDB based learning and supervised surrogate gradient descent technique. In the next class, we will cover this remaining topic of converting a trained deep neural network into a spiking neural network, and also look at some hardware implementations of spiking neural networks. Thank you very much for your attention. See you in the next class.